Up. So can you see my screen correctly?
Yes.
So thank
Fine.
you for your presentation. So I'm Pauline Delporte. I'm working as a research engineer at CES Group. It's a company in the south of France, in Toulouse. And I'm going to talk about how we can improve the modelization of flash flood events in urban areas by using high resolution hydrodynamic models, so physical models, or machine learning models. I'm going first to introduce the floods and their characteristics, then the challenge and the objectives of the study to modelize these kind of events. And then I will talk about our use case because we are working for this use case is used for the European project Extreme XP. Then I will explain my methodology with the general methodology and also the complexity of the data we are using, and then the scenario of use, because we can make the difference between different strategy of how I can use machine learning to facilitate the modelization of flash flood. So flash floods are floods created by heavy rainfall on a short interval of time. By short, I mean few hours to a day, but no more. It's a very quick event. This is also why it's very difficult to predict them and to modelize them. Due to climate change in Europe and everywhere in the world, we can observe an augmentation of events. So currently we have the storm called Boris, who cost the life of about 20 people during this September. I think you heard about it. It cost a lot of things to many countries in Europe. But climate change is not the only factor of the augmentation of events. It's also due to the urbanization, the land artificialization, and the river development. So due to that, we are increasing the consequences of flash floods and floods also. The damages are also as human and also economic. So this is why we need to modelize these events to anticipate the phenomena or to trigger action at the right time. By that we mean to move population, to put some new infrastructures, and linked to the two first points, we want to decrease and avoid the consequences. We are doing the difference between flood and flash flood. I'm talking only about flash flood because it's this kind of event we are interested in, but we can very do the difference between both. So a flash flood takes few minutes, a few hours, so minutes to days. It's very brutal. We cannot, without a good forecasting model, we cannot predict it. And it happens most of the time in area where you can find relief, streets and buildings. We can say that this event is local because it's only on a few square kilometers compared to plain flood which can be in a whole region. Due to the characteristic of the flash flood, because it happen in street, in urban areas, we need a very high level of details, so a good resolution. To model flash flood, we have some challenges because we have to have specific performances to be able to use in operational use. So we have some constraints on the model. First, traditional models we mean by that physical ones are based on all the physical parameters influencing the events. So by that we are talking about a lot of topographic elements, also the quality of the soil, a lot of physical parameters. So these data are numerous, they are very different from the one from the other, and sometimes they are very difficult to acquire. Because we have two difficulties. Or we are in a places where we cannot have the data because it's not available. For example, some place on the world we can not have a digital elevation model at at a high resolution. Or also sometimes organization or cities don't want to give us some information, for example, topographic information or weather situation. So it's very hard to have all this data for one place. And also the model is very difficult to tune. By that we want to say that we have a lot of parameters and all are interacting. So to find the right configuration, it can take a lot of a lot of time to test this model. So we have to, and so as we are talking about flash flood, it can be a bit constrained. And finally, the model execution is usually take a lot of time and also very CPU consuming. So in our operational needs, we want to use models in a crisis condition. And we can see that these constraints are very complicated to or in our situation because our event is very fast. So the model should be very fast as well, faster than the event at least. And we want to be able to re-execute the model because as flash floods are very fast and unexpected, we want to train different scenario, for example, different rain scenario. So we want to be able to re-execute the model very fast and to have a low CPU consumption. We can be very nice to be able to put it in different user and different computers. So we decide to use artificial intelligence to faster the inference and to be able to be used. We want our model to be used by a larger number of people and also non-scientist people, which is very important because we are talking about life. We are talking about also city organization. So it's very important that the model will be able to be used by different kind of people and not only scientists one. So we can work with AI in two different axes. First one is to work with still our physical model, but to add AI deep learning model or machine learning models to help the physical model to be faster or to be more precise. Or also we can completely replace the physical model by AI one. AI will bring several advantages. So the first one is that it will be more accessible in operation. It will be way faster because physical model can take hours to predict a flood map, and we hope that AI can be way faster. And it can also, which is very impossible with physical model, simulate unknown events. Imagine our AI model is well generalized. We can, on a different area we know, we can hope that if we have the data of a new place, it will also be quite precise and it will help us to modelize a flash flood in this new area. which is very not possible with a physical model, because physical model depends on a lot of physical and geographical parameters. So for that, to faster and still have a good modelization, we are working on two main axes. So the first one is to reduce the constraints on the input data with less data and maybe with a lower precision, because we have to accept to in order to be faster, to have a lower precision. And also we are going to work on our execution time by simplest operation, for example. But AI come also with some requirements. By that we mean a lot of data for the training phase, and this data needs to be various and have, if we want our model to be generalized. So it's another disadvantage. And we need data also to verify our result, because it's very important to be able to qualify our model if it is going well or not, because if you want to use in an operational way, we need to verify it. Our use case is used for a European project called ExtremeXP. So I'm going to quickly explain what is ExtremeXP. It's a big framework where we are assuming that training a model is a unique experiment. Unique in the way that it depends on the parameters, but also on the user. Because according to the user, we will give him access to some parameters or not. So we are saying that each experiment is unique, and this workflow is with machine learning models will create these unique experiments. And the improvement of flash flood is one of the use case among also other use cases, for example, like cybersecurity, mechanical problem prediction. So other use cases are working in this project as well. And which is very interesting is, as you can see on the graphic, that the user is in the center of the workflow in the way that he can interact according to his capability. For example, if it is a scientist, will be, or a hydrology engineer, he can comment some results. But if it is not a scientist, he will be able only to see the visualization, for example. So the user in ExtremeXP is very in the center of the loop, and we are dealing with different use cases to improve our models according to user. Our use case is concentrated on the city of Nîmes in south of France. We chose this city because of its special localization. So as you can see on the picture, it's close to the Mediterranean Sea and backed up by the Seven Mountains. And during fall, we have a large amount of warm water from the sea, which are blocked by the mountains. So because of that, they experience a lot of flash flood during the last years. The city is also particular because it's an old city with narrow streets. So we can imagine that we need a better resolution to be able to do the difference between two streets. Had a lot of residents and suffer from stress of urbanization. So we have a lot of streets, so ground very impaired viewsness. And also the natural drainage channel were partly obstructed by the year. This is also another explanation for why they are suffering from flash flood. We are working also with them because we could define they had data, for example, from they did a really good job of documented the last events, and they already have the operation modelization and forecasting models. They have different sensors, so like that we can have in situ values. And due to their vulnerability, they were also interesting to have a better forecasting model because of their condition and the availability of data. We could have enough data to train our models and to validate it with in situ, for example, in situ data. In the use case, we choose to work in a certain way. So we choose to work with a hydrodynamic model as a reference because it's very hard to have a in situ flood raster. It's very hard to have. So we know that our hydrodynamic model is working quite well. And in that way, we are able to generate the events that we want. So first, what we are going to do is to create a workflow with our hydrodynamic model with topographic data, flood events, and then to simulate with our hydrodynamic models. Once we have the outputs, these outputs will be used to set up our different AI models. It will be our ground truth and also our validation data. For the hydrodynamic model, the setup is very complicated because we have a lot of data variability. We have different various type and format. Various type, I mean by that in terms of format and type, but also we have raster, grid, or long temporal series. We have different spatial resolution, so we have to be able to synchronize all this spatial resolution because we cannot have a data with a 1 meter resolution and another one with 5 meter resolution. So it's a lot of interpolation. For example, we have to process this data first to have the same resolution and the best one. We also had to do some registration. As we are talking about geographic data, we need to have all the data at the same geographic points. So for that, we have a big part of our work is to do some registration. Sorry. We also are treating temporal data because we want to predict a flash flood, for example, in the hour or 8 hours later. So for that, we have to treat the data temporally. And we have to clean out data because some outputs can have outliers, for example, but if we are using AI, they need to be clean. So we made one of our job is a lot of data processing. Is it for the artificial intelligence models as well as the hydrodynamic model? To the hydrodynamic model create a grid. So every area, the area of interest is split in small triangles, and all the triangles must have the input data and output data. So we need all the registrations and the same spatial resolution. To set up our hydrodynamic model, we have different steps. First, we have to catch all the inputs. So for example, here we have the digital elevation model. a building mask, street mask, structures like bridge or hydrodynamic structures, the catchment boundaries, because we need our constraints at the limits also, and the inflows. They are processed manually, and then we are putting them together to create a grid. So this green part is the automatic process to create the grid which will be used by the hydrodynamic model. So the grid is all our small triangles with data, input limitations, and data at each little triangles. And then the grid is going to the hydrodynamic model called DAS flow. We are using this one in our case because it was developed also by a team in Toulouse. And we are doing the precipitation data. So this was the first. This one is the first setup. So it's only a physical setup, and it can take a lot of time with a lot of data, as we can see. And we also have a lot of manual processing, which doesn't really. It's not really what we want in order to be used in an operational way. In another scenario, we are using AI to facilitate the definition of input data. So we are still using the hydrodynamic model, but we're using AI to process the inputs. So for example, for the DEM, we can have a model which applies a super resolution. For the building, we can have a classifier, and as well for the street and the structures. Then the model is set up. We are putting the grid in the physical model, and then the outputs are compared to our reference, the first setup, so only a physical one. This is an example of our experiment. So what we want is to, from a low resolution, we want to go to the highest resolution. So from 5 meters, we want to reach 1 meter. It's very important because we are talking about urban areas, and in, for example, 5 meters of DM, we can miss a lot of details in a street. So it's very important to have also this one. Or we can also imagine that we want to predict a flash flood in another part of the world where we don't have this information. So we can use our AI model, our deep learning model, to reach a better resolution. So our data are from our point clouds or from IGN, and we have been tested different models because in the context of Extreme XP, we want to also be able to test different models, which is quite automatic in our workflow. So Extreme XP also allow us to see the different training of a large palette of models. So we have been testing generative adversarial network, convolutional network, and vision transformer. All our models are testing against the bicubic interpolation, which makes sense because bicubic interpolation is another non-AI way to have a highest resolution. So it's quite fast, it doesn't need training. And we are testing our model against the bicubic because if our models are doing worse, in that case, it doesn't make sense to use them. So the goal is to do better than the bicubic, at least. The second scenario, as I said during the presentation, we have two ways to use AI in our use case. First, it was to facilitate the input data processing, and now we want to replace completely the physical models. We only are using the input and the output of the hydrodynamic model as ground truth. So as input, we are taking topographic and meteorological information. By that I mean a building mask, a digital elevation model, of course, rainfall information, and the water depth, for example, at the starting time. We can see that we have less data than the parameters for the physical model. And it was very important to have that because our goal was to reduce the number of data as inputs. Then the AI model will predict 1 hour later the flood situation on the ground, and when we will be able to compare them to the hydrodynamic outputs and to have our loss function to the backpropagation or to define our metrics. When I'm talking about metric, I'm talking about different ones. First, the recall, so it's the ability to detect all the flooded area. But for that we have to define a threshold where a height where we are considering that the flood if the ground is flooded. So in our case, we are saying that a height that water depth more than 5 centimeters will be flooded, but this can be this threshold can be defined by the user. We are also working with the precision, so it's the efficiency to a model to predict correctly the flooded area. And another one, which is very interesting because it's taking into account both misses and false alarm, is a categorical index for evaluating the accuracy at a certain location. And then finally, we are using the accuracy, so it's the percentage of well-predicted pixels. We are using them to we are using this metric to compare the loss of accuracy compared to our physical model. So it's a percentage, but for that, we need to define an error tolerance. In our case, we define also 5 meters because we want to be quite precise in the definition of our water depth. So it was important to have a low tolerance threshold. This is an example of inference on NIM datasets. So our datasets have 5 meter resolution, but the resolution is not limited by our data or the general, but it's limited by the generation of our data. So physical models are taking like 8 hours to predict 8 hours of flood. So for 5 meter resolution. So if we are using 1 meter resolution, you can imagine that the grid we are using, the small triangles, will be smaller. So it will take a lot of time. And what we wanted first, it was to find the best AI model to do better than the hydro, to do faster and almost better than the, as better than the hydrodynamic model. But we didn't have a lot of time to generate as output for the 1 meter resolution. Maybe it will come. So as you can see on the left, we have our input. So this is the DEM, and the small square in white are the buildings. And here are the boundaries of the catchments, the big white parts. And that below it's our rainfall events in the hour. As output, our model is giving us a prediction on the right and the ground truth on the left. The ground truth is from our physical model, and the prediction is from our AI model. So we can see that the flood is quite well predicted. We can say that it missed some places here on the side of our tile. And sometimes also it tends to overestimate the depth of the water. But the accuracy is still to 92%. What was very interesting for us, it was the inference time, because as I said, hydrodynamic model will take 8 hours to predict 8 hours of the all catchment of Nîmes. And in our case, we have taken less than 1 second per tile on the GPU, of course. So we can estimate that for the whole Nîmes, for 8 hours, we will be able to take only a few minutes. I made another experiment on Zurich because the data were available online, and Zurich dataset has a particularity to have 1 meter resolution. So this is a DEM of all the city, the region of Zurich, and on the right I create the building mask. So as we can see, buildings are very important for the flood prediction because it's a very complex mask, and the AI model have to deal with these buildings. So we are doing the same thing for the Zurich dataset, and on the left still the DEM and the rainfall events. We can see that our model is doing better with a highest resolution because it has a better accuracy. It's also because we have a lot of scenario for Zurich dataset as well. And so we have a really good inference here. We can see that our model is able to detect and predict very small prediction, very located flood or water depth. As a conclusion, we can say that this use case is very challenging because of the data complexity and also due to its variability because between two cities, for example, we don't have the same resolution, we don't have the same data. Sometimes we can have the DM, but we don't have the building mass, so we have to process it. Or sometimes we don't have the water depth at the starting time. So our model needs to be quite generalized to every use case and every city. What we are trying to do for now is testing a new event in Nîmes because right now we have trained our model in 2 events, so 2002 and 2005, and now we are simulating modelizing the model with our hydrodynamic model, and then we will be able to use the data for the AI one. And also we have a new research point because for now our tiles are not connecting between them, and we know that a flood can have consequences from a tile to another. So it was important to research a way to encode the coordinates. So this is our work right now. And once we will have a very strong and accurate model, what we want to success is to have a model which can be used by different operators. For example, for a safety team to predict which street will be flooded, or for it will ease them to know the way for their intervention or to anticipate and to create some infrastructure to anticipate the floods, and also for the building parts. Indeed, we can imagine that the city a man who wants to build a building in a certain place, he can run the model, and like that he will be able to see if it's a flooded area or not. And finally, if we have a really good model, we want to be able to model area with unknown data. By unknown, I mean just ground truth, but with their DEM and their rainfall event, we will really want to model their flood if our model is enough generalized. I add some reference of our model. If you want, it will be available. And thank you for your attention. Do you have some question?
Hi, I have a question. Oh, sorry, there's already a hand raised by Svetlana.
Hello,
yeah.
Can you hear me?
Yes.
May I ask you about your start point to your prediction? Maybe it is a heavy rain started. And what is your start input data to do your calculation?
So, for the AI model or for the hydrophysic dynamic model?
I mean, if the heavy rain starts, what you can do with it?
If the rain already started, what we can say, we can have prediction of the rainfall in the hour and to generate the new flood raster. And as a starting point, we have the water depth at time 0, for example, because it's very different if we are taking a dry ground or if it's already flood in there. The prediction will be different. I don't know if I answered to the question.
Thank you.
We have, please raise your voice, Sahbaz.
Yes, exactly. Yeah, thank you. Yes, I have two questions. Could you go back to the slide where you were showing the metrics that you use to assess your model performance, the recall and precision? Exactly. So in this case, how do you define that a pixel is flooded? Yes, please go ahead.
For each pixel, we have a flood depth, a water depth. And we are taking this value and we have to define a threshold. So that's something that the user need to define. Actually, when we are doing evaluation, I'm testing different threshold. Like for example, 5 meters, 5 centimeters, sorry, 10 centimeters and 1 meters.
Okay.
And in that way, we have a classification in flooded or not flooded.
Okay. So in this case, you have the ground truth where you computed that there should be a flood, and then you compare it with if the pixel was actually flooded based on the criteria that you define, and then you compute the recall or precision in this case. Is that correct?
Exactly. Okay.
Okay. So in this case, I mean, let's how should I phrase this question? When you have false positives in this case, that for example, a pixel that was said that it was flooded, but in reality it was not flooded. Then in this case, I mean, do you have, for example, any benefit in having slightly lower precision, for example, that in the sense that there was a risk that there would be a flood, but in reality there might not have been a flood. I don't know if I point out my question correctly or if I explain my question correctly.
You want to say that in the case I only have false positive, but maybe I didn't. Can you repeat the end of your question, please?
Okay, so for example, let me give you an example. I work with forest fires mostly. Okay.
Okay.
So in this case, for example, when you have a false positive, that doesn't mean that there was not the danger of forest fire.
Yeah. Okay.
But for some reason, the forest fire did not happen because it's a very complex process. So in
Yeah.
this case, we actually, I mean, well, let's say we aim for a higher precision, but then it's okay to have a precision which is not too high. For
Okay.
example, if you, right, because in this case, from the point of view of operational, you should have some false positives because there might have been the danger of forest fire, but for some reason the forest fire did not happen. So my
Yes.
question is that if you have a similar situation in this use case,
Uh,
you yeah.
Thank you for your question. I understood. So we don't have that in our case because we are comparing our model against hydrodynamic model, and we don't really have a way to validate our hydrodynamic model. This is why it is very hard to say if it, because as you said, it's a false positive, but it could have flood. So for that, it's our next step actually. It's to compare to in situ value. But what we have now, when we have in situ value, is we don't have a map, a raster. We only have the water depth at certain geographical points. So this
Okay.
is what we want to do, but it's very hard to, because as you said, it's a very complicated process. So it's a study we have to do, but we didn't have yet look into the in
Okay.
situ and gauge value, for example.
Okay. And then you're also predicting the flood pixel by pixel in the sense that when you compute the recall, do you feed in the entire map in some sense, or do you do it pixel by pixel? In the
Uh,
sense that you give it one pixel as in when you do the inference, you predict the flooding pixel by pixel.
no, we are putting the entire raster.
Okay, I see. Okay. Okay. And then the next question was about the flight, which is I think next to it. Could you go to the slide, the next slide, please? Exactly. So I wanted to ask how I can compare these two. So on the left side, what do you have? And on the right side, what do you have?
On the left, I have the ground truth, and on the prediction, on the
Okay.
right, it's the prediction. So what I can do, but I didn't put it in here, but we are computed the mean square error, for example, or the absolute error to compare both of them, because we want to see when we are doing the difference between them, we can see where the model had difficulties to predict, and most of the time it's around the corner also, or close to building, or a lot of building areas. So this is my to say.
Okay.
It's I don't use it then like that when I'm working. It's because it's a good illustration to show to, for example, non-scientists people, and then we will project them on a map, and in that way they could, where we have the street and which street will be flooded, and it's also in extreme XP. People are working on the visualization tools, and they are trying to do 2D and 3D visualization. And this use case is one on they are working on to reproduce the building and to put the flood estimated in 3D.
I understand. Okay. Thank you for answering the question, and thank you for a very interesting presentation.
Pauline, there is another question on the chat.
Okay.
Do you see it from
Um,
Anin?
Do you think it's safe
Yes.
to totally replace trying to so I think, is it safe? That's a philosophical question almost. Yes, I think it's safe in the way that it depends on the use. Because if you want to just study the different flood areas, you can use the physical model because you have time. Yeah, it's so you can take the time to have the prediction with your hydrodynamic model. But if you are in an operation or in a crisis situation, we really cannot use the hydrodynamic model, because even if we are optimizing it, it will, for now we are trying to optimize it. It was taking like 12 hours and now it's taking 8 hours, so we already are working on that. But still, I don't think it will reach only few minutes, for example. So totally depends on the situation. If it's a crisis situation, I think AI is better, because like that you can, for example, test different range scenario and say, okay, if it is this scenario, I will have this streets flooded, this one. If it is another scenario, you will have this one, this one. But you're right in the sense that it's not a physical model. So if it's a very unknown scenario, maybe it will be better to try with the hydrodynamic one. I don't know if I answered to the question. The second one says, do you intend to improve your model to detect the missing places that you mentioned? Yes, we intend to improve our model with adding, for example, overlapping and the geographic coordinates, because what we can see that AI for now models are not really related tiles one from the other, and it's what we want to reach, because you can say that, for example, if you have a flood 1 kilometer away, it will have impact on the place where you are. So that's what we want to reach, it to relate the tiles between them. But I think it's a hard part for that, because we will need a lot of data. But that's the goal, and we hope that we will increase the accuracy on the corner, for example, on the side of the tile. Did you consider measuring uncertainty of your model and prediction? Not, because we have a lot of work to do also, but it's a very good point, because we could also have a map for the user with the uncertainty of the model, and like that the user will be able to trust the model or not. But I think it will come, but for now we haven't studied this point. You could.
Okay, are there any questions?
Yeah, so for the suggestion, Anine is talking about LSTM and transfer learning approaches for the performance. And actually, we tried LSTM, and our model is using attention layer. So basically, it's a unit for the spatial parts. We are using a unit like a segmentation model. And for the temporal aspects, we are dealing with attention layer. Like that, we have like a small memory of the events and the rainfall. And we tried LSTM. And transfer learning is what we are studying now, actually with the Zurich model, because we have a big model with Zurich, and now we want to see if with a small data of NIM we can have as well a good accuracy. But thank you for your suggestion.